Oh, that's why I waited. I'll do the pen after.
We're going to play technology like we did last time.
No, down. Technology has been a thorn in my side all semester, hasn't it? Come on. There you are.
I wonder how long it would take, how much it would cost to replace a projector.
That was zooming? Page width. There we go. There we go. There we go. Let's hit save. I'm sure we'll have to write stuff down. Okay, let's go back to the textbook. All right, so as we were saying, 2 videos on cross products. Understanding the geometrical idea of a cross product and then understanding it as a linear transformation. Okay? So, we know this formula, but of course you never calculate it that way, you calculate it this way.
Yeah, you can go block expansion.
Yeah. I like columns. So remember from chapter 3, the determinant of A transpose is equal to the determinant of A. So you can make IJK the first column, and U1, U2, U3 the second column, and V1, V2, V3 the third column, and you still get the same answer, right? Very nice. And that's where the determinants of the minors come into account. Okay. So one of the applications is the moment of force. Right? If we apply an application of a force, the moment of the force about A is given by the vector AB cross F. And you guys, I assume everyone here has computed cross products. You know how to compute them. Right. Because you did it in Calc 3. Or you at least did it in Physics 2. What? No, it's a determinant. It's nothing like matrix multiplication. Any more than dot product is like vector multiplication.
Cross product inputs, if you input 2 vectors, you get another vector, don't you?
Yep.
That's why we call it the vector.
That's why it's not matrix multiplication. But it's the determinant of this particular matrix you see right here, where the top row or first column are really vectors. And what's really happening here is you have a linear transformation from U and V from 2 copies of Rn to Rn that follows certain laws.
Oh, by the way, I've got a question on this.
Yeah.
Is this technically a true determinant? Because I thought a determinant was a scalar.
No, it's not a true determinant. That's why I want you to watch the videos, though. It's a linear transformation from Rn cross Rn to Rn. But it follows all the laws. Wait, okay, everybody came back. It follows all the laws of a linear transformation. But it also is computed simply this way. Yeah.
If we're asked to calculate the cross product on an exam, is this the only case where you're fine with us using the Laplace expansion, or do you still?
Oh, you have to use the Laplace expansion here, yeah. And remember, it's not the only case. If you have a row of mostly zeros and only one non-zero element, you can use the Laplace expansion along that row or column, right? If you got 0, 0, 0, 1, 0, 0, you can expand along that row or column. Okay, so yes, and this is a good thing you brought up. This is indeed the Laplace expansion of the determinant, or always using the row or column that has the illegal things in it, the vectors instead of scalars. Okay, and notice that the cross product of a vector with itself is the 0 vector. This is a true-false question that stumps many people. Is the cross product of 2 unit vectors a unit vector? True or false?
False.
False, because I cross I is what? 0.
Well, it depends on which unit they.
Well, the question was, is the cross product of any 2 unit vectors a unit vector? And the answer is no. Yes, I cross j is k, but they're only unit vectors when they're orthogonal to each other. If it's the same unit vector, it's not. But you could also remember that the cross product, the length of the cross product, is the length of I plus the length of the first one times the length of the second one times the sine of the angle. right? So if the angle's not 90 degrees, you're not going to get 1 times 1. You're going to get 1 times a fraction. And if the angle's 0, you're going to get 1 times 0.
Okay, so we're not saying a unit basis vector. We're just saying a unit vector.
Yeah, we're just saying unit vectors. I didn't say distinct orthogonal unit vectors. I think that's what most people think of as I cross J. Okay, the interesting thing about cross product is that it has orientation, right? The right-hand rule. So if you reverse the order of the cross product from U cross V to V cross U, the right-hand rule means it's going to point the opposite direction, right? And the negative of the vector is the vector of the same length but pointing 180 degrees the other direction. And the cross product of a vector with itself is always 0 because the angle between a vector and itself is 0, right? So it'll be of length 0, and the only vector with length 0 is the 0 vector. And again, either from Calc 3 or from Physics 2, you should already be familiar with these properties. And notice that it means it's multilinear. Notice when a constant multiple times the cross product of U and V is a constant multiple of one of them with the other, just like dot product, not both of them. Right? So it's multilinear in the same way that dot product is. Notice also, though, that cross product distributes over addition. And what is the product rule in Calc 1? The derivative of f times g is?
F prime G plus G prime F.
Yep. What about the derivative of two vector valued functions, u dot v?
Wasn't it?
It's u prime dot v plus u dot v prime. And what about the derivative of the cross product of two vector valued functions u and v?
Would it be U cross V prime plus V prime cross V?
No, it's just the same. It's u prime cross v plus u cross v prime.
Yeah.
The product rule is the product rule, no matter what we're talking about, whether it's scalar multiplication, cross product, or dot product. Isn't that one of the nice things about vector calculus is it turns out that the product rule is the same no matter which product we're talking about. So that's very nice. And the sixth one is called the triple product.
Oh yeah, wasn't this the one you used to find the area of the parallel pipette?
Yes, this gives you the area of the parallel pipette that is inscribed by U, V, and W. So if we have U and V and W, you get a parallel pipette, and the volume of that parallel pipette will be the triple product. And that basically boils down to the definition is the length of one times the length of the other times the cosine or the sine of the angle, and those cosines or sines will give you the correct heights for the parallel pipette. The triple product, for that reason, is used in Physics 2, right? For example.
I don't remember where I used it, but I know I used it.
Okay. Now, cross products are great. You should definitely watch the 3 Blue 1 Brown videos and review how to calculate cross products and how to calculate the moment given a force and a direction. But one of the more interesting uses in the 21st century of applications of inner products is least squares approximation.
Wasn't this one just the class?
Ah, this is a different kind. We're doing the same thing, but of course we're going to make it a little bit more complicated. So, computer processors, for example, they don't know anything about the trigonometric functions or any transcendental functions, including e to the x and log x. Now, quick question, why are sine and cosine called transcendental? A transcendental number is a number like e and pi. And, of course, the basic transcendental function is y equals e to the x, because the base is the transcendental number. But it's the base you need for y prime to be e to the x, for y prime to be equal to y.
Right.
And if you've had or you're currently enrolled in differential equations, you find it shows up all over the place for solutions to differential equations, so there was no avoiding e to the x and log x.
They're everywhere.
But if your second order linear differential equation a characteristic polynomial has complex conjugate roots, you get sines and cosines. And so sines and cosines are called transcendental functions. Why is that? Why are sine and cosine a transcendental function?
That can be written in terms of the x, right?
What is e to the ix?
Says theta.
Cosine x plus I sine x, right? And what is e to the minus ix?
And the same thing,
Cosine minus x, which is just cosine x, minus I sine x, which is sine of minus x. What if we add these two together? If we add e to the ix, sorry, I'm looking at a really oblique angle, plus e to the minus ix, what do I get?
Cosine, 2 cosine x.
2 cosine x. Of course, this is why Euler liked his number so much that he gave it his name, the Euler number, so that's why it's E for Euler.
This reminds me of Heisenberg.
Yeah, this gives you cosine x. There you are.
I had two numbers in cosine. Euler's constant, Euler's number.
No, that's the same thing.
Yes,
You're talking about the Mascheroni constant?
there's a constant that,
Mascheroni constant, the Euler-Mascheroni constant, yeah.
yeah.
It has its name too. Okay, so this is cosine, but what if we subtract them? E to the ix minus e to the minus ix. What do you get?
2I sin x.
2I sine x. So we divide both sides by 2I.
Oh, that's the definition of cosine.
This is the definition of sine and cosine. This is the actual, honest-to-goodness definition
I completely.
of sine and
I
cosine.
thought it was defined based on the Taylor series.
Yeah, but it's the Taylor series of e to the x. So the three you're supposed to recognize are e to the x,
I loved this when I back in calculus.
which can be written as a limit of polynomials,
Right.
right? Remember, each one of these, so let me write it out properly. The limit as n gets large without bound of a bunch of polynomials in Pn plus 1,
Yeah.
because k equals 0 to capital N of x to the k over k factorial, right?
Right.
Which means that e to the ix is the limit as n gets... Okay, so we'll stop writing the limit part, so we'll understand that I'm supposed to be writing the limit part, but I'm going to be lazy and just put an infinity up here, which means limit. And now I get ix to the k over k factorial, right? But what is I to the k?
It depends.
Either I or negative 1.
Yeah, I to the 0 is 1, I to the 1 is I to the 2 is negative 1, I cubed is negative I, and I to the 4th is 1 again. So if k is 0 mod 4, then I get a 1. If k is 1 mod 4, I get an I. If k is 2 mod 4, I get a negative 1. And if k is 3 mod 4, I get a negative I, right?
Right.
Okay. Does this series converge? Absolutely.
I'm not sure how to deal with opening series tests when I have all that knowledge.
Okay. Page new. I knew it was going to take 2 days to do this. Okay, so we have the ratio test, which is part of Calc 2. So it's in our prerequisite. And we compute
What we're doing the ratio, I thought we were doing AST.
the limit as k gets large without bound of the absolute value of a sub k plus 1 over the absolute value of a sub k. And if this is a finite number, in particular 0, in fact, if it's a number less than 1, then it converges absolutely. And if it's greater than 1 or equal to 1, well, if it's greater than 1, it diverges. And if it's equal to 1, then it might converge, but if it does, it converges conditionally. All right, so we have the limit as k gets large without bound, the absolute value of x to the k over k factor, plus 1. Lost my spot there. Could you do Control Z? k plus 1 factorial, x to the k plus 1, divided by the absolute value of x to the k over k factorial. Now, what we're going to do is when you divide one fraction by another fraction, you invert and multiply. So this is the limit, as k gets large without bound, of the absolute value of x to the k is the absolute value of x to the k plus 1 factorial, k factorial, divided by the absolute value of x to the k. This gives us the limit, as k gets large without bound, of x over k. Now, k is the thing that's getting large without bound. K may be 6.02322 times 10 to the 23rd, but it's the same number all the time in this limit. So what is this limit? What is the limit of a constant over k as k gets large without bound?
It goes to 0.
0, which is definitely less than 1, so it converges absolutely.
Wait, how did you deal with the complex term?
Absolute value of e to the ix is 1.
Of IX?
Cosine theta plus I sine theta, the length is cosine squared plus sine squared, which is 1.
So the absolute value of I is 1.
The absolute value of e to the ix is 1. E to the ix is on the unit circle.
Okay.
It's a unit vector. Okay,
Oh,
so that tells us that one of the things we can do, because we now know that it converges absolutely, is we can take the limit of this sum, k equals 0 to infinity, of ix to the k over k factorial, and write it. And this is what Euler did, as the k equals 0 to infinity, and k is odd, of ix to the k over k factorial, plus the sum. In fact, let's do it the other way around. This is the way that most people do it. They do the even ones first. And this is not a delta, it's a 0. K even, sum, k equals 0 to infinity. Oop. K odd of ix to the k over k factorial. Now, if k is even, isn't I to the k 1 or negative 1?
right.
And if k is odd, I to the k is I or minus I.
Right.
And I can describe all the even numbers by using the integers from 1 to infinity, 0 to infinity, and using ix to the 2k over
Yeah. Yeah.
2k factorial.
Yes, you can.
And I can get all the odd ones by going from 0 to infinity
2k plus 1?
and using I to the 2k plus 1.
Or 2k minus 1, I can't remember which one it was.
It depends on whether or not you start at 1 and 0 or we're starting at 0. So we have to go plus 1 because there's no negative 1. 2 times 0 minus 1 would be a negative 1, and we would not get the right indexes. Okay. Now, we're ready for some good...
Oh,
I don't know what's going on here.
I think I know what we're doing.
No, I'm talking about my pointing devices fighting with each other again. Okay. So this becomes the sum, k equals 0 to infinity, of minus 1 to the k, x to the 2k, all over 2k factorial. And this isn't 2k factorial, it's 2k. Now, why did I change I to the 2k to I minus 1 to the k? Because,
I squared is negative 1.
right, where, there you go. I to the 2k is I squared to the k, which is negative 1 to the k. And I can do the same thing here. What I'll do is I'll write I to the 2k plus 1 as I to the 2k times I. right? So I get the sum k equals 0 to infinity of minus 1 to the k times I times x to the 2k plus 1 over 2k plus 1 factorial. And I should have done that here too. Now, when I add e to the ix and e to the minus ix, I'm adding 4 infinite series, but they all converge absolutely. 2 of them subtract out, and then 2 of them add up, right?
Right, you cancel them.
Because when I put minus x over here, I can distribute that minus sign out here because it converges absolutely, and I can distribute this I out because I know the series converges absolutely. I had to fix that first. So I get 2 times the sum, k equals 0 to infinity, of minus 1 to the k, x to the 2k over 2k factorial. And now you know where the e to the ix plus e to the minus ix over 2 gives you the series, the Taylor series for cosine. If I subtract them, then the first 2 series subtract out. And when I put minus ix in this one, that minus 1 in the I will be out front. And so I'll get 2I times the sum, k equals 0 to infinity. And remember, I can only distribute the I and the minus 1 because it converges absolutely. X to the 2k plus 1 over 2k plus 1 factorial. This is what Euler did.
Is
Yeah.
2k supposed to, right there, supposed to be in parentheses factorial?
Yeah.
It's supposed to be the quantity 2k factorial. And what's that on top of the summation?
Infinity.
Okay, is that meant to be like minus, what's the sign, the little dot right next to it?
It's an artifact of the pen of Windows trying to flare. When I'm trying to, I keep turning flaring off, but then Windows does an update and turns flaring back on again. Yeah.
This is a little bit off topic, but is using this complex exponential stuff the most accepted way to prove the identity that sine squared plus cosine squared equals 1?
In all.
No, the most accepted way is to use the Pythagorean theorem because on the unit circle you have cosine theta plus sine theta equals, right? You have cosine squared plus sine squared equal 1. But this will also prove it. Yeah.
Although the last time I remember, my version of sine did not have any complex.
What?
When we did the Taylor series for sine, the last time I remember, did not have a complex number in front of it.
No, this is new. The complex numbers in there is new. That's why we're doing it. Okay. But that should explain to you why the definition for hyperbolic cosine is e to the x plus e to the minus x over 2. And the definition of hyperbolic sine is e to the x minus e to the x over 2 minus x.
It's the complex part.
Yep. It's the real part of sine and cosine. Okay? Because technically sine and cosine and e to the x are functions of a complex variable. You can take complex analysis for engineers, for example.
I can stick an I.
E to the ix, that's a complex number. So sine and cosine and e to the x are functions of a complex number, not a real number. But if we take the real part of the complex valued cosine, we get hyperbolic cosine. If we take the imaginary part of the real sine function, you get hyperbolic sine. What's even more interesting is that we think is sine and cosine, are they periodic?
Yeah.
Is e to the x and log x, are they periodic?
No.
Oh, they only look that way when you look at the real part. If you take complex analysis for engineers, you find out that e to the x and log x are periodic.
In the complex.
And sine and cosine are not. As functions of a complex number, they're not periodic.
What can we look up to look at that?
And just Google it.
Google complex.
Yeah, complex valued sine and cosine and complex valued logarithms.
So
Or e to the x.
Do those live in the complex plane?
Yeah. We've already defined e to the x and sine and cosine x for complex numbers. It's right here.
Ah. So I can take sine of 2y.
What's even more interesting is that it means that sine and cosine are a limit of polynomials. So, how did we handle infinite polynomials in our classes, or how do we handle them in an engineering application, or how do we handle them on a computer? We can't add up an infinite number of terms. So what do?
You can integrate it and then not have to deal with that.
No, we would still have to deal with it. What do? On a computer, anybody had any programming yet? On a computer, or in a real-world application, we can't add up an infinite number of terms. So what do?
Do a partial sum?
What?
Do a partial sum then.
Okay, you use one of the partial sums. Yes, we stop. We truncate. Sine is approximately the sum k equals 0 to 51 of x to the 2k plus 1, minus 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. And you have the Taylor remainder theorem.
That one's the one that gives you the error.
Yeah. It gives you the error bound. So, on an interval, x minus delta to x plus delta, we can find a c in the interval so that sine x is exactly equal to the truncated sum. And what is this truncated sum? It is a polynomial, right? A polynomial of degree n.
What's the little thing that you have up there on top of that sum? What's that?
51?
Is that
51.
that's 51?
Yeah, I used 51 just as a number, okay? But any n will do. And then we have x to the 2k plus 1 over 2k plus 1 factorial plus the Taylor remainder, which is going to be the n plus first derivative of sine evaluated at c over k factorial times 2 delta. Okay? So, this C comes from, Taylor proved this, and it comes from the intermediate value theorem for continuous functions. Okay. So what's this do? Computers don't know anything about transcendental functions because E itself is an infinite process. It is a number whose decimal approximation never terminates and never repeats. So it can't calculate E any more than it can calculate pi, or sine, or cosine, or e to the x, or log x, or any transcendental function. So what does it do? It approximates it with a polynomial that's really close.
Is that delta right there?
And there's a 3 blue 1 brown video you need to watch this weekend on Taylor series. It's not in the essence of linear algebra, it's in the essence of calculus series. Really, really good one to watch. Yeah.
Is that delta right there?
Yes, it's the delta in the x. It's the length of the interval from minus delta to plus delta.
Yeah. I remember seeing the Taylor remainder theorem, but it's been a long time.
Well, yeah, it just looked a little different because I used the interval from x minus delta to x plus delta.
Because if I remember-
Usually they think they do delta over 2 or
Yeah.
h over 2,
Yeah,
and then they
okay.
put an h where I have the 2 delta.
That's what I've seen, and also I've seen it where you also want to calculate the max error.
Yeah.
So you
Well,
get the maximum value.
the reason this works is because remember that if a function is differentiable, it's continuous. And a continuous function on a closed bounded interval attains its maximum. And the absolute value also attains its maximum. So this is bounded by some biggest number. In reality, you know that there is some c which is that is true. But you replace this value f, the n plus first derivative of c, with the maximum of the n plus first derivative of c
Yeah.
on the interval from c minus x minus delta to x plus delta.
That's
And that
right.
gives you a slightly bigger error. But it's a bigger, for error, being slightly bigger is okay. Because if the slightly bigger one is fine, then the real one's fine, right?
So you can't actually ever calculate the real error?
Oh yeah, you can. It just takes a whole lot more work. And using the maximum is better. And what is the maximum of sine and cosine on any interval?
1 and -1.
So you replace it with a 1, right?
Which is okay. That's a lot more convenient.
Yeah. You know that it's going to be less than that, but it's somewhere between 0 and 1, so you just replace it with a 1. If we're talking about sine and cosine. But tangent and secant and cotangent, those are a little bit more difficult. But now all of a sudden you see, wait a minute, computers are in fact are really great when it comes to polynomials, because elements of Pn can be represented by a list of numbers, the coefficients. And does everybody remember synthetic division?
Yes.
Okay, so we got to know. Where are we?
Then,
Are you talking about partial fraction
wait,
composition?
No, I'm not talking about partial fraction decomposition. Hold on. Let me get a new page here.
are we talking about that synthetic division as in the other way to write polynomial long digits?
If we want to divide x cubed minus 1 by x minus 1, we would write out 1x cubed plus 0x squared plus 0x minus 1, and we would divide by x minus 1. I think I need my straight line drawer here. So we bring down the first coefficient, and 1 times 1 is 1, and 0 plus 1 is 1, and 1 times 1 is 1, and 0 plus 1 is 1, and 1 times 1 is 1, and the remainder is 0. So we know that x cubed minus 1 is x minus 1. Now what is this polynomial here? 1, 1, 1. It's x cubed plus x, it's x squared
It's x squared
plus x plus 1. So if you represent your polynomials as lists of numbers, like computers do in Pn, it's easy to divide one polynomial by another. But we also have the remainder theorem that says that that remainder is equal to the value of the function at x. Yeah,
Good question. Where were we supposed to learn this? Because I don't recall ever. learning-
high school algebra.
Yep, that didn't happen. I've not used.
I learned it somewhere around 7th grade.
I've avoided.
5th grade, actually,
I
5th
didn't
grade.
learn that this existed until college, until not one. So.
I had a,
I didn't learn this existence of college algebra. What I did was polynomial log division the traditional way.
okay.
Because that works for any polynomial.
So basically, if I divide a dividend, p of x, by a divisor, d of x, and I get a quotient, q of x, plus a remainder, r, and if the divisor is a binomial, it's ax plus b, right? Then the remainder will be a constant, because it has to have a power less than ax plus b. Then the division algorithm says that the dividend, p of x, is equal to, and by the way, I wrote the remainder wrong. Yeah, the remainder divided by d of x.
Yeah.
Then q of x times d of x plus r, right? This is the division algorithm. So if I want to know, am I at the bottom of the page already? I didn't think so. If I want to know the polynomial at a, I divide by x minus a. And the polynomial at a is equal to the quotient at a times the divisor at a plus the remainder. But what is the divisor evaluated at a? If the divisor is x minus a? 0. So you get r, the remainder. So if I divide by a using this synthetic division, then the remainder I get will be the value of the polynomial. And I didn't have to calculate x to the 27th or x to the 51st. All I had to do was multiply and add 51 times. 52 times for a polynomial of degree 51.
And
And so I don't have to worry about overflows or underflows. So if the number was 0.003, then 10 to the minus third to the 51st is 10 to the minus 153rd, right? And if the number was 5,280, I don't want to raise that to the 53rd power. Whereas if I use synthetic division, I never have to do that. I can calculate each sum along the way, and I get the right answer. And using synthetic division to evaluate a polynomial at A is called Horner's method. And this is what all computers use.
is there a way to write that in terms of linear alpha?
Well, actually, we just did. Yeah. But you have to go down the length of your list of numbers in your vector and Pn, right? Okay. You have to use a for loop because until you add the coefficient to the next intermediate number, you don't know what to multiply by. So let's take another look at an example. If I have the polynomial x to the fourth minus x cubed plus 2x squared minus 3x plus 7, what is P of 2? So in computer language, the transpose of the vector that represents this polynomial in P5 is 1, negative 1, 2, negative 3, 7. And I want to know the value at 2, so I'm going to divide by x minus 2. No, another 1. 2 times 1 is 2, 2 minus 1 is 1, 2 times 2 is 2, 2 plus 2 is 4, 2 times 4 is 8, 8 minus 3 is 5, 2 times 5 is 10, and 10 is 17. And the Taylor remainder theorem says, so x minus 2. So I get x minus 2, let's see, I get x squared minus x cubed plus 2x squared minus 3x plus 7 is equal to, did you quit moving around, is equal to x cubed plus x squared plus 4x plus 5 times x minus 2 plus 17. Right? And the remainder theorem says is if I plug in 2, no matter what x cubed plus x squared plus 4x plus 5 is at 2, I'm multiplying it by 0. Right? So I know the answer. It's 17.
Oh, I've never had synthetic division. It's a
Khan Academy is your friend here, and it's pretty easy.
South Con is
You're going to love synthetic division. It's pretty easy. Now all of a sudden, representing complicated functions, especially ones that involve logarithms or e or any trig function or any complicated function like square root, right? Roots, cube root, 52nd root. Representing them by approximating with their Taylor series becomes really important.
So this is the part they were missing when they taught us about Taylor series.
No, they taught you about Taylor series so that I could talk to you about this. They taught you about Taylor series so that we could have a similar discussion in your difficult class. And why there's an entire chapter of difficult in which all the solutions are infinite series. Because as it turns out, if you have a nonlinear differential equation, then you don't just get e to the ax plus e to the bx, right? You get where a and b are the roots of the characteristic polynomial. If it's nonlinear, then it's probably not possible. There are lots of situations where we can find an exact solution. But usually the solution is some infinite series. In fact, sine and cosine are really infinite series, just like e to the x is. They're not. We just gave them a name because we use them all the time, right? But we can't give a name to all of the uncountably, infinitely many different absolutely convergent Taylor series there are. Now, we give some of them names like Jacobi polynomials and Bessel functions because they're infinite series that are solutions to very important differential equations that are used often in engineering and physics and chemistry. If it gets used enough, Hermite polynomials, Chebyshev polynomials, Fourier series, Then we give them names. But most of them, the overwhelming majority of them, do not have a name, right? I mean, we couldn't possibly give them all names. We only have 26 letters. Right?
And there's only
Most of them would have a name that had an infinite number of letters in them. So that's just not possible to give them all names. So we just have to deal with series all the time. And this isn't a burden for a 21st century engineer or scientist because computers represent everything using series and polynomial approximations anyway. We just truncate the Taylor series high enough up so that the Taylor remainder theorem says that the remainder is less than the error we're willing to accept. And if we're talking about empty, I actually did this. So an empty boxcar for a train weighs 40 tons. Empty, it weighs 40 tons. Okay, within a few feet is plenty. Within 3 meters is plenty of accuracy of knowing where that thing is because it's not moving if it's not going to move. If it is moving, you aren't going to stop it. Right? Its M is way too big to change its V. Okay, but if we're talking about trying to design the surface of a computer chip, now we need 10 to the minus 23rd, 10 to the minus 22nd. So we have to have a lot more terms in our Taylor series so that the remainder is far smaller than that. Does this make sense?
So, if I heard correctly, there was a way to calculate the number of terms you needed in your Taylor series to achieve a certain level of accuracy.
Yeah, use the Taylor remainder theorem. It's there. We saw the nth derivative, the n plus first derivative in there. You can, if you know what the derivative is, you could go backwards and figure out what derivative you needed to get there. And there was also an n factorial in the denominator. So you solve for the n factorial. Now it's a nonlinear problem to solve, but that's why finding the zero of a function becomes super important. Anyway, right now we're talking about polynomial approximations. So what are we really doing? We have this infinite dimensional vector space. All of the continuous functions on the interval from 0 to 1, or minus pi to pi, or 0 to 2 pi, right? From A to B. And we're going to project them onto the subspace of dimension 4, or dimension 12, or dimension 51.
Oh, this is a vector projection?
Sure it is, right? We want to find the least squares polynomial of degree n that approximates cosine or sine or e to the x. We're going to project that function, infinite dimensional vector space, and we're going to have a finite dimensional subspace, which you can think of as a plane, and you're going to project that function down onto a point on that plane. But that point is not really a point, it's a polynomial of degree less than n. Does this make sense?
So by approximating the polynomial, we were just projecting from so we were projecting from a higher dimensional.
An infinite dimensional vector space.
Right, the infinite dimensional vector space of all continuous functions.
Onto a finite dimensional subspace.
And then we project it onto the polynomials in this case.
In this case, yes, Pn. The polynomial is a degree less than n. Does this make sense?
Okay.
So projections becomes the 90% of what you're going to do after you leave college, if you're using mathematical models, is ordinary differential equations, statistics, or partial differential equations, and how are you going to implement it? Using projections, using approximations. The question isn't whether or not you're going to project it onto a finite dimensional subspace, because of course you are, because we can only compute algorithms that stop in a finite number of steps. We can't wait until God is old to get the answer. We have to have the answer, in a finite number of steps. So we will always project these complicated functions, like the 3-body problem, the Earth, the Sun, and the Moon. Right? It's a nonlinear differential equation. It's well known. It's a nonlinear ordinary differential equation. It's in your Physics 3 textbook. Right? Yeah. A-bomb. Relativistic physics.
Oh.
Where I went to school, we called Physics 3 A-bomb and Physics 4 H-bomb. Anyway, because it had only 2 syllables, okay? It was easier to say. Anyway, and it sounded edgier too. And this was during the Cold War.
Fun.
That's the biggest reason why I got those names. Just remember, I went to school during the Cold War, so. It isn't a question of whether or not we're going to do this projection. The question is, which finite dimensional subspace do we choose? And a lot of times we will choose Pn. N could be 18, 17. A lot of times it's 18. You just need the first 57. If you're trying to approximate sine, cosine, and logarithm to, or e to the x to 16 decimal places on the interval from -1 to 1, it turns out that you need a polynomial of degree 17. But remember that on a computer, that's just a list of 17 numbers. And using Horner's method, you just multiply, add, multiply, add, multiply, add, multiply, add, multiply, add, multiply, add, multiply, add 17 times, and that gives you the answer.
Which is a really easy.
Which in a computer takes microseconds, right?
How does it deal with factorial though?
It doesn't have to, because we're only going to 17.
Oh.
We pre-compute the polynomial. The coefficients of the polynomial for e to the x and sine and cosine are already hard-coded into the chip physically, right? Because it's just a string of ones and zeros. So it's in an area of CMOS, right?
Oh, so we don't even have to tell, we don't even have to go make it compute the factorial?
No,
It
no.
already
It
has-
knows the coefficients of the polynomial of degree 17 for most of the common transcendental functions, and it just pulls it out of a register that's been. Now, if there's a bug, it can be updated, because you can update modern chips because they are CMOS, right? But it's just stored in a location and kept there all the time in permanent memory. In rewritable programmable memory, double EEPROM. Okay, so the double E means electrically erasable, programmable read-only memory, right? And you don't want to update your chip's firmware too many times, because double EEPROM memory only electrically erases and rewrites successfully a finite number of times. It's just a large finite number of times. You don't want to do it every week. All right. So, now, what I hope this discussion did for you is it motivated you to understand why performing the least squares approximation of a transcendental function using a polynomial by projecting that function onto the finite dimensional subspace Pn is so important. Okay? And it's not just important to computation itself. When we store music or video on a permanent storage, that file can't be an infinite size. When we stream, the stream can't be an infinite number of ones and zeros. So what do? We choose a basis. A basis, let's just talk about MP3 and MP4 for the sound only. We have chosen a specific basis of sounds, right? Usually this basis of sounds, each one of them is referred to as a sample. This is a word from the 80s, so they may not still use that term. And that projects all the music and the voices and the things that we can produce with the speaker, that it picks up off of the microphone, it translates it into using fast Fourier transform into a digital signal, and then it projects that digital signal onto this finite basis. That's why what's in the file is a finite number of coefficients. Each at 8K or 16K, so 16 kilohertz, you have for each 1/16,000th of a second a vector of numbers, and those are the coefficients of the basis vectors, right, that are stored in the codec. And when you combine them using a linear combination, you get what comes out of the speaker. And what comes out of the speaker is very close to the analog signal that it recorded. It's just not exactly the same.
It's not supposed to get it with the amount of processing power.
With the technology and the processing power we have available to us, yes. Okay, so it took us most of the semester, but now we're into the 21st century, right? This is what we do. And I was really fortunate because this all began in 1981, right before I graduated from college in 82, and started my graduate career in 83. Because in 1981, the IBM PC came out, and not as well known, Texas Instruments started shipping this brand new chip called a DSP, or digital signal processing chip. Right? Your phone has at least 5 of them in it. What does a digital signal processing chip do? Well, it has the codec in it. It does the fast Fourier transform of the analog signal, and it takes the digital fast Fourier transform and translates it back into the digital signal. And it does all that using something we're going to talk about on Tuesday called the fast Fourier transform. In other words, it takes the time series sample of the sound, which is a finite number of points, and multiplies it times a matrix. Because a projection is a linear transformation, right? So it's represented by a big matrix, a big square matrix. So it multiplies the vector of sound samples by this matrix, and then it gets the vector of frequency samples. That's what the DSP chip does, and that's all it does. It goes back and forth. Either multiplies by A or it multiplies by A inverse.
Okay, so and that's how we deal with the ADC from
Yeah.
ADC?
Yeah. ADC is analog to digital conversion. And then the other one is DAC, which is digital to analog conversion. Okay? And right before the electrical ADC for the speaker and the DAC for the speaker, between that, the computer and that is the DSP chip, the digital signal processing chip. And since that had just came out, and a couple of years later I had just finished my master's degree in mathematics, in pure mathematics, then it was easy for me to get lots of jobs because none of the other engineers took linear algebra, much less Fourier analysis, unless they were an engineer and they kind of understood Fourier analysis, but they hadn't had linear algebra yet. And so I was in a perfect position to do all the programming and to do all the mathematical models to develop things like modems. Okay. And I did not go into sound and video processing. I went into telecommunications and networking. Okay. So, and you guys are in the same position, but instead of applying this to telecommunications and networking, you're doing machine learning and data mining, right? And artificial intelligence, right? So, this is another good time to be finishing your degree in the next year or 2 or 3 or 4. All right, and so what's happening? This is kind of a weird picture. The real function is f, and we're going to approximate it with a polynomial, g. And what is the distance between f and g? Remember our norm. Okay, if we use the inner product, the Euclidean inner product, then our norm, the inner product between f and g, is going to be the integral of f of x times g of x dx, right?
Yeah.
From a to b. But what is the distance between f and g?
Are we talking about
Well, the distance squared, and by the way, the distance squared is the inner product of f minus g and f minus g square root. Oh, I put distance squared, right?
right?
The distance squared is the inner product of the vector with itself.
Yeah.
So you get the integral from a to b of f of x minus g of x times itself dx. Right? But this is a somewhat more costly length than we really need. And remember we talked last week about the fact that while every inner product gives us a norm, there are lots of norms that are not derived from an inner product. If we don't care about angle, we only care about length, then we could use a norm that doesn't come from an inner product. And by the way, this is the 2 norm, right? Because where it's the square root of the sum of the squares?
Yes.
This is the Hilbert norm, or Euclidean norm.
I think I've heard about Hilbert, maybe.
A Hilbert space is a complete inner product space.
Okay.
Complete means that it not only includes all of the things that in the linear combinations, but all limits of things in the linear combinations. So you're using limits as well as sums. Yeah.
Is that related to the concept of Hilbert curves, like
Yeah.
spatial curves?
Yep.
Fractional dimension.
That's going even farther and deeper into theoretical mathematics, but yes, and it's very cool. By the way, I love that stuff. Anyway, my undergraduate advisor was Kozlov Stenijevic, who was a Serbian measure theorist. So yes, we did lots of abstract integration theory. Okay. He spent World War II as a member of the Black Hand. He spent all of World War II collecting up. He would be given a group of pilots that had been downed over the line, German lines, and then his job was to smuggle them over the lines into France where they could be picked up by the British so that they could get back into their plane, a new plane.
Wasn't the Black Hand also the group that killed
Ferdinand?
Yeah.
That would have been his parents' generation, though, but yes, they did. Well, okay, but who hired them to do it? Who hired the Black Hand to assassinate Ferdinand, and why was it so easy to convince the Black Hand to assassinate him? France. But Ferdinand was the king of the area that included Bulgaria and Serbia. And they didn't want to be under a king. They wanted to be a free state, like the United States. So if you have a king and you want to be a free state, what do you got to do? You got to get rid of the king, yeah.
Or you could do whatever the hell Britain did.
But you needed the resources necessary to accomplish such a task. So somebody had to give them lots of money to buy weapons illegally, right? And smuggle them into the country. Okay. Now, France claims that they called off the assassination and that they're completely innocent. But Kozlov tells me that by the time France had decided that they didn't want to do it, it was too late to contact the people that were in place to do it. There was no way to contact them. It's not like we had cell phones. This was, right? It was the 1931, so, or 29 or 30.
No, this was 14.
Oh yeah, World War I. This was World War I. This was 1914. We were still using pigeons, okay? So there was no way to tell them not to do it. It was way too late. Okay, so where were we here? It was interesting having an advisor who was a Serbian. Okay. Now, we talked about other norms. Remember, in Rn, we had the 2 norm, which was induced by the inner product of U and V. And this was the sum of the products of the corresponding elements. But remember the 1 norm? And remember the P norm? We did talk about this, right?
Yes.
Yes.
Okay. Just making sure I'm not remembering a different semester.
Yes, we did talk about different norms.
So what would the 1 norm be in the vector space of continuous functions from A to B?
It would be the sum of.
To the 1 over 1th power. The P norm would be, that's a little hasty. And so the distance between f and g in the one norm would be the integral from a to b of the inner product of f and g, of the norm of f minus g.
Oh, so it's just the absolute value of the area between the curves.
Exactly.
That's what I think it would do.
Well, yeah, but I want you to understand it in terms of linear algebra, not just know the definition, like, okay, it's the absolute value of the area in between. I want you to think of it as the one norm distance between f and g, because it's the fact that we're minimizing the distance. We want the polynomial that's closest. We want to minimize this distance you see here, that they call area, which is the one norm of f minus g. It is the distance between f and g in this normed vector space. If a vector space has an inner product, it's an inner product space. If a vector space has a norm, like L1, then it's an a normed space. If it has an inner product, it's a Hilbert space. If it only has a norm, it's a Banach space.
Huh.
Banach, B-A-N-A-C-H. So, the continuous functions from A to B with the Euclidean norm is a Hilbert space after a mathematician named David Hilbert. And I don't remember what Banach's first name is. But if we use any of the other infinite number of positive number integers p, and we use any other norm besides p equal 2, so we'll put a little 2 here. And we get a Banach space. Now, yes, if p equals 2, it's still a Banach space. Every Hilbert space is a Banach space, but most of the Banach spaces are not Hilbert spaces. Right? So I can erase the p equal 2 because both men's names work just fine. But we usually refer the term Banach space to simply say that it's normed, but it's not the one that's induced by the inner product, so it's not a Hilbert space.
So it would be correct to call it, so that it should call the Q norm the Hilbert Banach space.
The what?
The Hilbert Banach space.
Oh, no, No, that'll make it too complicated. Yeah. Okay. So, couple of things. We now know why we're going to go to all this trouble, because our 21st century technology is rooted in it. Okay. We now know what it is we're looking at and why it's linear algebra. Because we are, amongst other things, projecting the infinite dimensional vector space of continuous functions on the interval from A to B down onto the polynomials of degree less than n, Pn. And by closest, we're going to use the one norm. Okay? We could use the two norm. But as it turns out, if it's one norm closest, it's also two norm closest. In fact, it's p norm closest for all the positive integers p.